Hi everyone, welcome to the section 6.3 video series. And in this section, we're going to continue solving differential equations with power series solutions. But in this section, we're going to be able to learn how to solve these differential equations with power series about singular points. Okay, so if you could recall from section 6.2, where we were finding power series solutions about ordinary points, meaning like nice values. Well, we're going to be able to solve differential equations with power series solutions about these not nice values, these specific x values that give us domain issues. Okay, so that's the goal for this section. Okay, so we have a couple learning objectives. We want to be able to define regular and irregular singular points. Okay, so we're going to be using singular points and we're going to branch out what's a regular and irregular singular point, what's good to use, what's not good to use. We're going to establish the Frobenius theorem, which allows us to solve these differential equations with power series solutions about singular points. And then we're going to use all this to solve second order differential equations using the Frobenius method. And then we're going to define and use the indicial equation. Okay, so that helps us out when we're solving these differential equations with our power series. So let's remember our goal. Our goal in this class, our goal overall is to solve a differential equation, and specifically a differential equation that looks like this, second order and variable coefficients, right? Functions of x. And so similar to last section, we want to put this into standard form. Okay, so that means we're going to divide by this a2 of x, the function that's attached to y double prime. So we're going to get y double prime naked. All right, and so when we do that, what we obtain is y double prime, some function p of x times y prime, plus q of x times y equals 0. Okay, so like I was saying before in that section 6.2, the last section we covered, is that, we were able to solve for any values that were nice, all right? Nice meaning there are no domain issues or other type of issues like that. Okay, like dividing by 0 or some type of natural log or any imaginary numbers, things like that. Okay, so we were able to find nice values and solve around those types of values. But in this section, we're going to learn how to solve around these singular points, the not nice values, where we would have domain issues like dividing by 0 or like I was saying. So we're going to learn how to actually solve a differential equations with power series centered around these not nice domain issue x values. And that's where the Frobenius theorem comes in. Okay, so if x is a regular singular point of the differential equation, then there exists at least one solution of the form y equals x minus x naught raised to the r times the power series c sub n times x minus x naught raised to the n. Okay, so we're at least guaranteed one solution of this form, at least just one solution. We're always guaranteed that. All right. So this is quite a lengthy, solution. So what we want to do is distributing this x minus x naught raised to the r and combine it with x minus x naught raised to the n to just combine this power series right here, where it's just c sub n times x minus x naught to the n plus r. Are much easier to write. Okay, and so there is that new variable r, right? R is just a constant, so don't worry about it. It's not a specific type of variable that we have to deal with. It's a constant R, and we're going to be able to determine what that's going to be. We're going to be able to determine it within the solution of the problem, and then We're also able to use a shortcut where we can determine like what the R values might be with the initial equation. That's one of our learning objectives from up above, the initial equation, but we'll get there. But we're able to solve what R is, all right? And then the series will converge for some values from our center to our radius of convergence. So just a couple notes about the Frobenius method, what it entails. So for the sake of this intro to differential equations class, right, it's still an introduction class. We're just going to be expanding about the singular point x naught equals 0. All right, it just creates a much simpler solution for us as we're starting out. So, our solutions will look something like this. I'm going to use A sub n. I just prefer that one better than C sub n. But A sub n, and it will just be like x minus 0 raised to the n plus r. But, we would rewrite that as n equals 0 to infinity, A sub n, x to the n plus r. Okay, so that's what we would be using for our solutions, for our power series solutions, okay? Um, Once you take higher differential equations class like upper division or grad school, like you start expanding about not x equals 0, like x equals 2, x equals 5, x equals pi. But here we're going to keep it simple, which is x equals 0. And okay, so a couple other things. The only difference in this method, as we've seen like in chapter 6, is that we have that unknown exponent, and we're going to go ahead and find it for each problem. So, that unknown exponent r. We have to figure out what it is because it's part of our solution. And that the Frobenius theorem, it guarantees only one solution. So we for sure can get one solution. But we know for a second order differential equation, meaning like, y double prime, we'd expect two linearly independent solutions. But the Frobenius method sometimes only gives us one. So we could expect two, but sometimes we only get one. Sometimes terms cancel out, things go to 0, and we're only left with one solution. So that's okay, just as long as you're doing it right. And so there are some technical requirements that determine when that happens. So don't want to get too much into it, but here's a link here below. You can click it on the PDF, and it should take you to a write-up that discusses this requirement. But yeah, we're basically guaranteed to one solution. We're pretty much going to get two of them. It just depends on how the problem turns out. So yeah, we're going to get two solutions like y equals C1, times some power series plus C2 times some, I guess I could write Y1, C1 Y1 plus C2 Y2, where C1 or where Y1 and Y2 are like power series. Okay, so that would be like our general solution. But that's the setup. We're introducing Frobenius th method. We're introducing what our expansion would be, right, for our solution. And we would go ahead and start solving these, okay? So there's a couple things we got to get through, like singular points. What's a good singular point? What's a not good singular point, like regular, irregular? But we'll get through that, and then we'll start trying some examples, okay? So thank you for watching. I'll see you in the next video. Take care.